Okay, hello everyone. My name's Anna. I'm an SI leader at SDSU for Physics 196. This problem, I believe, is on your homework if you're taking the course right now, and I thought it was kind of a weird problem. So hopefully, you guys, me going through it is helpful. I don't think there's a ton of online resources for a problem like this, so I thought I'd make a video. All right, without further ado, let's get into it. We have a 2.4 centimeter cubed box with its edges aligned with the xyz axis, and it's in an electric field given by this equation, 400x plus 140 I hat, Newton coulombs, where x is in meters. What is the net electric flux through the box? So first things first, I'll go ahead and I'll write out our electric flux equation for the electric flux through any surface, right? The electric flux through a surface is equal to the electric field vector at that surface multiplied by the area vector at that surface multiplied by the cosine of the angle between them. So hopefully everyone's familiar with that equation and this isn't a big surprise. Now it tells us that we have a box, and with its edges are aligned with the xyz axis, we'll go ahead and kind of put our xyz axis here. We'll say that's y, we'll say this is x, we'll say that's z. And what it's telling you basically is that the corner of the box is at the origin, and it kind of like extends positively through each of the axes directions. So our box kind of comes out. Oops, I can draw better than that. Doop 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 doop. It's not going to be perfect, but oh well. I'm not much an artist. There's your box. And we're trying to find the electric flux through it that has been created by this electric field. And your electric field is given by kind of a funky equation. It's given by 400x plus 140 I hat. Okay, so if you remember from Calc 2, I hat is a unit vector. It dictates the direction. So as a quick review, let's give a new coordinate system, x and y. It's 2D. You have some force vector, and the magnitude in the x direction is 4, and the magnitude in the y direction is, let's say, 3. If you were to write this force vector out in terms of its base unit vectors, you would write it out like, here's your force vector, it's equal to 4i hat plus 3j hat, right? Because I hat dictates the magnitude in the x direction, and j hat dictates the magnitude in the y direction. So if we're comfortable with that concept, then we know that this electric field is going exclusively in the x direction, right? Because there's no j hat, there's no k hat. K hat would dictate the magnitude in the z direction. It's purely, the electric field is going purely in the x direction. It's like that. But we have this variable here. Okay, well, if the direction is set, you know, there are two parts to a vector, right? There's the magnitude, and then there's the direction. Hopefully this has been beaten into your head by like a bajillion times by now. If this is your direction, then I mean this equation is dictating your magnitude of your electric field vector. And if it has a variable in it, then that means that it changes as you move across the x-axis. Your magnitude gets bigger as you move across. So if your x coordinate is equal to 0, then pretty intuitively we can say that the electric field line at that point, let's say at the origin, is going to be equal to 140. If your x coordinate is equal to, I don't know, 1, then your electric field vector at 1 is going to be equal to 540. If that makes sense, because then you would have 400 plus 140 would be 540. So the electric field gets bigger as in magnitude, not in direction. It gets bigger in magnitude as you move across the x-axis. That's basically what it's trying to tell you. I'll go ahead and get rid of this, and we'll get right into solving it. Oops, I have to deselect. Haha. Alright. So this is the equation for the electric flux through a face. So we have 6 faces on this cube, right? Let's look at the face up here, right? The top face. Its area vector is going straight up, right? We're familiar with that. The area vector is always normal to whatever face you're solving for. So it's going straight up. So the angle between your area vector and the electric field line, which again is going exclusively in the x direction, that's going to be equal to 90 degrees. And cosine of 90 is equal to 0. And so you don't even have to plug in the electric field or the area vector magnitude quantities. You just kind of know your electric flux through the top surface is going to be equal to 0. You can say the same for your bottom surface down here, because it follows a similar logic, right? 90 degrees. What about this surface over here, that one that's closest to us? Well, its area vector is going something like that, right? It's going straight at the y-axis. Your electric field is, again, perpendicular to it, so you don't have to worry about the electric flux through there either. The only area where you have to worry about the electric flux occurs at this face right here and the face in the back. So it's these two faces. And we'll go ahead and we'll label them 1 and 2, and we'll solve for each of the electric flux through those faces respectively. We'll start with the first face, the face in the back that we can't really see. All we have to do is kind of plug in numbers to the equation at this point, right? So we say the electric flux is equal to E. So we'll put the equation in, 400. What's our x-coordinate at this face in the back here? What's your x-coordinate? It's 0, right? It's not going in the x direction. So we'll say that's 0 plus 140. Okay, sweet. So that's E taken care of. What's A? Well, A stands for area. Area of the surface is going to be equal to 2.4 centimeters squared, right? That makes sense because this is 2.4 centimeters and this is 2.4 centimeters. So we'll go ahead and we'll convert that into meters. 0.024 meters squared. And we're comfortable with that. I just moved the decimal places over two places to convert into meters. All right. So now all we have to do is multiply these two numbers, here and here, by the cosine of theta. So we'll say cosine. And what's theta? It's the angle between your area vector, which is popping out here because it's perpendicular to the surface, and your electric field vector, which is going exclusively in the x direction. And since they're going in directly opposite directions, the angle between them is 180 degrees. And if you plug that all into your calculator, you're going to get a number something like negative 0.08064, and this is in Newton meters squared per coulomb. That makes sense. Newton per coulomb is your electric field, meters squared is your area. So there you go. That's the electric flux through your first face. Awesome, we're already halfway done with the problem. Let's solve for the electric flux through our second face. And again, we plug in numbers. Let's write out the equation for our electric field line. Our x-coordinate has changed because now we're up here, right? We're up on the secondary face. And your x-coordinate is going to be equal to 0.024 meters. That makes sense, right? Because that is the width of your cube, 0.024 meters. There you go. You can see the decimal place. So that's how far it has been extended in the x direction. And add that to 140. All right, great. So that's E. What about area? Well, same as last time, right? 0.024 squared. This would be meters squared. And now we multiply that times the angle between those two vectors. Cosine of what? Well, our area vector is going perpendicular, right? So it would be going this way in the x direction, as is our electric field line. They're pointing in the exact same direction, so the angle between them is 0. And if the area times the cosine will kind of give you a solid number, and if you multiply that in 2 times, one times 400 times 0.024 and the other times plus 140, you'll get, and I'll keep it in 2 different numbers just so it's easy. You'll see it'll cancel out more nicely, but you'll get a number such as this, 0.0055296, something along those lines, for multiplying this whole part of it times this whole part of it, it gives you that number. And you add 0.0864 when you multiply this whole part of the equation into your 140. And I kept it different because, as you can see, this part and this part are exactly the same. And that's nice, because when we're solving for the total electric flux through the cube, right, that's just equal to the electric flux through each of the faces, right? The sum of each of the electric flux. Here, I'll write this out nicely. The sum of the electric flux of each of the faces. So let's add the faces we have electric flux for up. It's just 1, right? You're plus 2. And these two numbers cancel out, the 0.08064 numbers. And you're left with your total electric flux for the whole cube is equal to 0.005296 Newton meters squared divided by coulombs. All right, I hope that was helpful, and good luck with the homework, guys.